3, 2, 1. Alright, and away we go. Another 2070 video. Alright, so today we're going to keep looking at orthogonal sets, and in particular, we're going to look to project into them. Alright, so let's get right to it. Given a subspace with an orthogonal basis, then for any element y in Rn, so note y doesn't need to be in W, I'll define its orthogonal projection to be the following. All right. Now, note, that formula should look a little familiar because, hey, if y was actually in W, this is what y would equal, right? That's what we talked about last time. So, that's pretty interesting, and I bet there's some other interesting things going on here, so let's talk about them. Right, so obviously, first thing to note is that the projection of y into the subspace W is, in fact, in W. It's a linear combination of elements in W, so it belongs to the subspace. That's precisely what a subspace is. We cannot escape by scaling and adding. All right. Furthermore, note that the projection is y when y is in W. As we established last time, if you belong to the span of an orthogonal set, then you're equal to that formula, where you're scaling by these particular dot products. Right? We justified that formula. And so note, what we're doing with the orthogonal projection is basically going, well, there was nothing special about y belonging to W. This computation can always be done. So you can always find this thing. All right. So, all right. Now, let's talk about some other neat things, and this one is the neatest of the neat. If you take your orthogonal projection and subtract it off of y, you'll actually end up in the orthogonal complement of W. Now remember, this is the collection of things that are perpendicular to everything in W. W is spanned by the V1 to the Vm, so if the dot product of this with any one of those is 0, then you're perpendicular to everything in W, because everything in W is a linear combo of those. And again, you just simply dot product this expression right here. Okay, and see that indeed you'll get 0. Just work out the details, remember how dot products work, and you got it. All right, now, equipped with all of this wonderful information, we now get the big answer for today. The real reason you care about orthogonal projections, and honestly, the real reason we care about any of this orthogonal stuff, the distance between y and its orthogonal projection is less than or equal to the distance between y and any element of W. In other words, the orthogonal projection of y onto W is the point in W that is closest to y. So now we have a technique of, given a subspace, as long as I have an orthogonal basis, I can take any element and get it into that subspace and do it as efficiently as possible, in the sense that we are as close to that point as possible. So for example, let's say we had a subspace we really wanted to be in, like, oh, I don't know, the column space. And if we weren't, well, now I have a way of getting in there and doing so as best that I can. Probably minimizing, I don't know, some sort of like ax minus b or something like that. I don't know. Anyway, so let's actually justify this, and this has got the argument for this is super slick. I always thought this one was super cool. All right, so take any element that's in W. Note that this is a linear combo of things in W, so it remains in W. And this here we just verified is in W perp, so their dot product is equal to 0. All right. Now, when I look at the distance squared of this quantity, now recall when we first talked about distance, I noted that you always want to look at the distance squared because there's a lot more you can do with it. And we rewrite this distance as this distance instead. Note that I'm sneaking in a plus 0, the dirtiest math trick in the book. By law of cosines, we know that this quantity squares into this piece here, but hey, these are orthogonal, so that drops out. And hey, that looks like a squared plus b squared equals c squared. I wonder if this is secretly the Pythagorean theorem. It is. All right, and now that we know that this quantity always has to be less than or equal to the sum, because this is a non-negative thing. and we know that's equal to this, and thus square rooting both sides gets us that indeed the distance from y to its projection onto w is always less than or equal to the distance of y to any element of w. So we have indeed the point closest in the subspace to y, and furthermore, this gives us the actual distance between y and the subspace, right? Because y minus any element of the subspace is always less than or equal to this, so that's how far away you have to be. Beautiful. All right. Equipped with that knowledge, let's do a quick little computation to play us off. All right, suppose we have a subspace W spanned by these two elements. Note those elements are orthogonal to each other, easily verified by taking the dot products. All right, now let's consider an element Y, 3, 1, 5, 1. I can compute its projection, and again, it's just a matter of computing a bunch of dot products, scaling, and then adding. All right, and in this case, I pick up a 3, negative 1, 1, negative 1, like that. Pretty neato. All right, and then now, if I want to compute the distance between y and the subspace w, you just need to take the difference of this and that and compute its length. And in that case, you get this, and the length is a big ol' square root of 24. All right, and that's the story. So, there we go. We have now talked about the orthogonal projection and verified that it indeed gets us the thing closest to any our element into to the subspace. Pretty cool. Right, and as I kind of already mentioned, it'd be great if we could always do this. So given any subspace, compute its orthogonal projection. Well, so far we've only established that you can do this if you have an orthogonal basis, so we need a way of creating such things. Perhaps that's what we'll talk about in the next video.